in CAE Associates Ansys e-learning series. The webinar is going to be on damage of fiber reinforced composites. CAE Associates, we're an engineering consulting firm in Middlebury, Connecticut, specializing in finite element and computational fluid dynamics. We've been an Ansys channel partner since 1985 and have developed this Ansys e-learning series to help maximize your software investment. Be sure to visit our website, which includes an extensive resource library with over 250 items in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of experience in performing finite element and engineering analyses. We also offer an extensive schedule of Ansys courses taught in our Middlebury office. If you need help deciding on the best course for your application, be sure to visit our CAEA University page. And the complete library of these e-learning recordings is available for viewing in our resource library and also on our YouTube channel at www.youtube.com/CAEAI. If you're licensed PE in New Jersey or New York State and you wish to obtain PE credit for your attendance, we ask that you attend the entire webinar, participate in all the polls, and complete a short survey that will be emailed to you at the conclusion of today's presentation. If you have any questions during the presentation, please use the Q&A window or the chat window in the WebEx, and I will address them at the end of the webinar. So today we're going to talk about modeling of damage in fiber-reinforced composite materials. And there's really two main methods of looking at damage or failure in composites. We can look at the actual fiber or matrix damage, when we actually have failure in the fibers themselves or the matrix. And we can also look at delamination, which is the separation of the fibers between the layers. So first, let's take a look at delamination and how we would model that in Ansys. So delamination involves a simulation of basically a crack that will propagate along a known path. And there are two methods available in Ansys for determining whether a crack is going to propagate. And they are the virtual crack closure technique, or VCCT, or cohesive zone model, CZM. And these techniques work well for the modeling of delamination because it's a crack essentially that's propagating along the path between two layers. Both of these methods require the use of special elements, essentially elements that define that interface, the layers where the crack is going to propagate. So the first method of looking at delamination would use CZM. CZM, or cohesive zone method, involves basically a maximum allowable stress, at which point the interface will start to fail. And then we can either specify a maximum distance at which the failure is complete, or we can specify an actual energy, which would be the total energy under this curve, in which the failure would be complete. If we load up and unload, we'll actually unload along this slope and reload along that slope to complete the delamination. The other method of determining whether a delamination is going to propagate is VCCT. VCCT was initially developed to calculate the energy release rate of a cracked body. And it's widely used in crack growth simulation of laminate composites. Again, the crack growth has to be along a predefined path, and none of these techniques are going to predict the direction of a crack. It's going to assume to propagate along a known path. And with VCCT, we perform the VCCT calculation to calculate an energy release rate. We compare that to a critical energy release rate for the material, and we can determine whether the crack will grow or not. Both of these capabilities are available in Workbench now. If we insert in the tree, we insert a fracture item in the tree, and then under that fracture item, we can insert a delamination via either contact elements or interface elements. Contact elements is pretty easy to set up. we basically choose a contact pair that we want to allow to separate. That contact pair has to be bonded and has to use the penalty method. And for contact elements, the only method available to determine debonding is CZM. And the CZM properties are going to be entered in engineering data. CZM material involves, like I said, a maximum stress, maximum tensile stress, either a total distance over which the debonding takes place, or the energy under the curve, under this area here, for the debonding. The initial slope here is actually the stiffness of the contact elements themselves. The contact stiffness represents the initial slope. The other method of modeling delamination is to use interface elements instead of contact elements. Interface elements are connected between the two sides of the model that are going to separate. Therefore, we need to have a matching node pattern on each side of the interface. So if we insert an interface delamination in Workbench, there's two methods of determining the matching nodes. You can either have used a mesh matching item under meshing and just choose that match control item here, and it'll use that match control to determine the nodes that match. Or we can simply identify a source and target surface and tell it, look for any nodes that are within this tolerance of each other on each side. For interface delamination, we can use CZM, just like we could for contact. However, there's different CZM materials for interface elements versus contact elements. They each use different CZM materials. Interface elements allow for the same bilinear definition of CZM, but they also allow for an exponential definition of CZM. And the interface elements also allow us to use the VCCT technique. VCCT, it doesn't require any material definition. It simply requires a critical energy release rate. And it also needs to know essentially where the tip of the crack is. So in addition to inserting an interface delamination, we also have to insert what's called a pre-meshed crack. And a pre-meshed crack is simply a name selection that identifies the crack front and a coordinate system that the crack acts in. So we really have two methods of setting up delamination in Workbench: interface elements and contact elements. Which one to use really depends on your situation. Interface elements generally give better convergence behavior. They allow for the use of VCCT as well as CZM, and they also allow for exponential as well as bilinear CZM. And they can also use what's called viscous regularization to help with convergence. Contact elements are certainly easier to set up. We just choose a contact pair. We don't require any kind of matched mesh. We can have an arbitrary mesh on each side. And the contact elements allow for standard contact behavior after separation. So if this part was going to close back down again, the contact elements would still be there to prevent those two surfaces from passing through each other. And in general, the post-processing is easier with contact elements. I mentioned viscous regularization. This is a new feature in version 15 where we add basically this sort of damping into the model that helps with convergence with these interface elements. Here's an example. If we put a viscous regularization of 1e⁻², we get this problem, this three-point bend test of a double cantilevered beam. It converges in 412 iterations. If I reduce the viscous regularization to 1e⁻⁵, you can see I get a much sharper drop. Here we actually have some slope here due to the viscous regularization. When I reduce that, I get a sharp drop, but of course it took a much greater number of iterations. Without any viscous regularization, the problem here as posed actually wouldn't converge. We couldn't get this to run to completion without including that somehow. This viscous regularization currently is only available in MAPDL, but it could always be added as a command block in Workbench. So let's go and take a look at how you would define this in Workbench. I have a pretty simple model here in Workbench. Open this up and take a look at it. So we have these two beams, and I brought it in, and if we look, there's actually two contact regions here. Contact region between these two areas and contact region between these two areas. Now what I want to simulate here is that this is going to be my initial crack, and I want to see if the rest of this is going to separate. So let's see how to add a delamination in Workbench. So I'm going to insert a fracture into the tree, and in there I'm going to insert contact debonding. So I have a contact debonding. I simply choose the contact region that I want to be able to debond, and that's this contact region. And if you notice, for some reason it stayed yellow. Generally means there's some kind of error in Workbench. And the reason here is, if you remember, I mentioned that the contact has to be bonded, and it also has to use the penalty method. It's the only method allowed for interface debonding. The next thing it wants is a CZM material. That's done in engineering data. So if we just jump back here to engineering data, we can add a new material. We'll call it CZM contact. And we'll go down here for cohesive zone, and we'll add a separation distance based. And we'll say that there's when the normal contact stress is 10,000, and this thing separates by 0.03 inches, we'll say that the debonding is complete. We can also, for each of these CZMs, it's the normal direction. We also have a mode 2 debonding available, which would be the tangential direction. So we'll just put something in there. We'll say that's a little higher. We'll say it goes a little further. And we also here allow for a little bit of artificial damping. We'll put a small number in there. So now, if we go back, we'll refresh this. Now I can choose here my contact debonding material, and that's really all there would be to do. Actually, that's not all. I want to make sure that this region is not bonded. I would want to make that frictionless. And then I would go ahead, and of course I'd have to set this up as a nonlinear problem, set up automatic time stepping, turn on large deflection, and I can run it and see this debond. If we wanted to, let me just show you quickly, if I delete this one, we can also insert the other method, interface delamination, and we'll give it a critical energy release rate. And we can either choose a matched meshing control, or in this case, I'm going to choose node matching, and I'm going to pick a source and target face. So if I go in here, and I pick this as my source face, and I'll go in here, and I'll actually pick this as my target. And it needs one other thing. It needs a initial crack. So the other thing we have to insert here is what's called a pre-meshed crack. The pre-meshed crack wants a name selection. So I actually need to choose a line here. I'm going to pick a line. I'm going to create a name selection, and I'm going to say it wants a name selection of nodes, so I'm going to say, well, we'll go ahead and create this name selection of crack line. Oops. Right there. And there's a new feature in 15 that I can take this, and I have a line. I'm going to create a nodal name selection from that. So if we rename this quick, crack nodes. And now if I go back to my pre-meshed crack, I can pick that name selection, and that tells it this is the crack front. I would want to use a coordinate system as well. I'm going to pick that line again, and I'm going to create a new coordinate system, and I'm going to rotate it 90 degrees about X. And now I want to tell it that this pre-meshed crack uses that coordinate system. So now we can see that the crack looks correct with those nodes. And interface delamination, we tell it to use that pre-mesh crack I created, and there we have it. Set that up. If we actually went and solved this, we would see that, just open up this other model here. Oops. Oh, it's already open, sorry. And if we look, we can basically see how this thing delaminates, and if we look at the force reaction, we can see that the force increases, but as the thing starts to delaminate, the force needed drops off. Force needed separated drops off. So that is delamination modeling in Workbench. Now let's take a look at another method of modeling damage in composites, and that is really in-plane or fiber and matrix failure. To determine if a composite part is going to fail due to fiber or matrix failure, we can really simply calculate the stress in the part and compare that stress to some failure criteria. Failure criteria in Ansys that are available are maximum stress, maximum strain, Puck, Hashen, LARC 03 and 04. And these failure criteria are really just methods of combining the stresses to determine if failure is going to occur. If you happen to use ACP to do your composite modeling, ACP will allow for the plotting and failure, different failure criteria and the layer in which it occurs in. So the worst failure criteria and the layer which occurs in. So very easily determine which layer is going to fail and due to which criteria. If you use MAPDL, MAPDL has a command, the FC command or failure criteria, to define the failure criteria, FC type to activate a specific criteria, and then you can plot the failure. Basically determine which elements exceed that failure criteria. Workbench, as far as evaluating failure based on the stress level that you've already calculated, is really limited to using the stress tool to compare the maximum stress to a specified value. We can get a margin of safety for a stress value. However, in many cases, just because a certain element has exceeded some failure criteria doesn't mean the part itself has completely failed. It means that single location has undergone some kind of fiber or matrix failure. But what happens then? When a small region fails, what happens to the rest of the model? And the way we look at that is via a progressive damage model. Progressive damage model allows us to evaluate how the failure is going to progress through the entire model under a certain load. So instead of saying, well, there's a certain stress, these elements have failed, let's look at what happens when those elements do fail. So we can include progressive damage in our analysis, and for it we specify failure criteria for the tensile and compressive directions for both the fiber and matrix. We give it the failure criteria: is it a maximum stress, Puck, Hashen, etc. And the technique requires that we specify what happens to the model when it fails. What happens to those elements when they're failed, and that's called the damage evolution law. So the term progressive damage really refers to the spatial progression of damage through the model. As one element fails, what happens to the rest of the elements? The only available damage evolution, what happens to those elements after the damage, is called instant stiffness reduction. Basically, we say that when the stress reaches the damage limit, the material is immediately, the stiffness of the material is immediately reduced to a user-specified value. So this is how the damage will progress through the model. This progressive damage is available in Workbench and requires, like I said, three things. We require the material strength limits, the damage initiation criteria, basically what criteria to use to determine whether damage is going to occur, and the damage evolution law. What happens to the material after damage occurs? And you can input that all under engineering data. Then, after we solve the analysis, we have, under post-processing, we have a new item, damage. Once you insert damage in engineering data, you'll actually get a post-processing capability of damage, and we can look at different things. We can look at the individual failure criteria. We can look at the maximum failure criteria. We can look at the damage status, and the damage status is basically 0 or 1. It's either not damaged or damaged for an element. So let's take a look at a model here. We have a plate with a hole. We put it under load, and if I go in and I say, okay, which elements become damaged, we can see that these elements have become damaged and their stiffness has been reduced by half. Let's take a look at that actually inside of Workbench. So if I go into this Workbench model, I have a plate with a hole, and I've got a kind of shearing load applied on here, a tensile end shearing load to kind of shear it and then put it under tension. And I've already solved the problem. And in this problem, if we bounce back over here, we've defined material strength limits. We have tensile strength in the X or the fiber direction and the Y and Z directions. We have compressive strength in those directions. We have the damage initiation criteria. In this case, I'm using a puck damage criteria. And we have the damage evolution law. What happens to the material after it becomes damaged? So if we go back to the model, and we want to go in here and insert under damage, we can look at damage status, see which of these elements, and it shows us, okay, that's where the damage has occurred. And notice the damage is either basically 0 or 1. We can look at the maximum failure criteria. And you can see that we have the failure criteria ranges all the way up to 5.6. If you want to figure out which failure criteria is actually used, we can insert the individual ones. I can look at the fiber tensile failure criteria. And you can see, well, that occurs over here, but that's not quite that 5.6 value. If I insert a damage of a matrix tensile failure criteria, then we can see, okay, well, that's where the maximum occurs, is actually going to be in a matrix failure. And if we insert the damage, and we can look at the matrix damage variable, and this tells us that the stiffness in the matrix direction here has been reduced by 0.6. One of the things I usually do when I'm looking at damage is I like to look at the unaveraged results. So we can change to unaveraged results here. And you can see which of these elements have been reduced, or which really nodes have been reduced to that 0.6, and show that damage has occurred. So that's how we would use Workbench to evaluate damage in the matrix and fiber directions. As I mentioned, the only method available in Workbench is the instant stiffness reduction, but in version 15 in MAPDL, Ansys has added the capability to include what's called a continuum damage model. And rather than being completely damaged instantly and dropping to that new stiffness, we have a continuous increase of damage. Therefore, damage can progress within an element as well as through the mesh. This method is only currently available in MAPDL. So if we look at that plate with a hole, we can see the damage variable here is not one number or another, but it's a range of numbers from 0 to 0.83, which is the maximum damage achieved here. And if we look at those different methods, the continuum damage model, you can see that we have a continuously changing amount of damage or change in the stress strain curve, whereas the other method, the immediate stiffness reduction, basically we have a change in slope. We had some initial slope, and we now have a new slope that we're proceeding along.